Hello everyone, thank you for joining today. My name is Manam and today we're going to be looking at the states of matter. So a few of our learning objectives include to understand what are the different states of matter and to be able to model them and to also define internal energy and also be able to draw and interpret changing state graphs. Now it looks like a lot of learning objectives, but all this stuff is really intuitive and so it shouldn't be too much of a challenge for you guys. Let's get right into it. Okay, so you can see on my screen now that I have three different squares. We're going to use these three different squares to represent the three different states of matter. So first of all, let's have a look at what those states of matter actually are. So the most common one that you see all around us, right, are solids. Then we also get liquids. Then we also get gases. Okay, so you might sometimes hear gases be called the gaseous state. Either way, it doesn't really matter. It's talking about the same thing. So what we also know is that all three states of matter are also linked. Now, what are they linked by? They're linked by something called a physical process. So a physical process is when you do something to a solid, liquid, or gas to change it into another state of matter. Okay, so we're gonna have a look at those very soon. But first, let's have a look at what sort of like substance are we going to use to represent a solid, liquid, and gas state. So we're going to keep it very simple, and we're just going to look at plain old H2O, right? Water. Now, what we need to understand is that the world around us is made up of very, very, very small, so small that you can't even see things called atoms, right? Now, these atoms can be arranged in several different types of ways, and the way that they are arranged represents what sort of state of matter they're in. Okay, so if we have a look at the atoms within a solid, so this would be ice, right? So that's a solid form of water. All of our particles, right? I'm going to use the word particle and atom interchangeably. A particle can really be used to talk about one single thing, and this thing in this case is an atom. So don't get confused if you hear me switching words here and there. Okay, so the atoms in a solid are all very neat and ordered, right? They're all lined up very closely, right? And you can sort of think of this like soldiers at their base, right? They're all neat, they're all ordered, they're all very, very rigid. Okay, they're stuck in their positions. So I'm going to not go fill up this entire square, although it's going to take ages, but I'm going to fill up halfway and you understand that. So let's label some properties on the side. Okay, so atoms in a regular lattice. So that's a brand new word there. This arrangement of things in a sort of like grid, right? That's called a lattice. Okay, so atoms are arranged in a regular lattice. Atoms are fixed. Fixed. Okay, so that's really two things I need to understand about solids. So because the atoms are fixed, they also can't move past each other, which sort of makes sense, right? And atoms vibrate. Okay, so that's just a property of all atoms. The vibration of the atom talks about its kinetic energy. Its kinetic energy describes its temperature. Okay, so that's just a little bit of extra information for you there. So that's ice. Now, what would happen if we were to melt ice? So that's our very first physical process. I'm going to do that in black, right? Just because it's easy. Okay, so if we were to melt ice, so we were to apply heat, these ice molecules from a solid form would now go into a liquid form. Now, how are the atoms arranged in a liquid form? Well, in a liquid form, the atoms are slightly organized, right? But they're also a little bit chaotic. So whilst they're still kind of close together, right? You can see that here. You can see that they're not in a regular lattice anymore, right? There's not 3, 6, 7. There's not 7 to a row anymore, right? There's 3, 4. There's 6 on the bottom row. There's only 2 on the middle row, like that, right? They're not regular anymore. They're a bit disordered. So let's write it down over here. So atoms in irregular lattice, but now this is the very important bit that students often forget. They're still close by. Still close by, and also the atoms are no longer fixed. Atoms are no longer, oops, that looks like H, no longer fixed. Now that they're no longer fixed, that means that they can move past each other. Now, this is the property that actually allows liquids to flow. Like when you have a glass of water and you tip it, the liquid water inside actually flows out of it. Why is that better? That's because the atoms can actually move past each other. That means that they can flow, so the atoms can flow out of your cup. That makes sense, right? Now, what would I have to do to a liquid to turn it into a gas? Well, that would be the normal term that most people use is called boiling, but really we're scientists, so we're going to use the technical term, which is evaporation. So if you evaporate a liquid, it will turn into a gas. So let's write that here for our physical process. Evaporate. Okay, and let's highlight that as well, just so it's very clear. Now, when we evaporate our liquid, we add energy into our atoms. Our atoms get very excited, right? They get a huge amount of kinetic energy in their store. That means that they vibrate faster and faster. Now that they vibrate faster and faster, they can put a huge amount of distance relative to solids and liquids between each other. And that means that the atoms are no longer in any form of lattice. No longer in lattice. Very spread apart. They have very high energy as well. High energy. What? High kinetic energy. Let's say that. High kinetic energy. And that's really all you need to know about the three main types of states of matter. Now, let's have a look at it the other way around. How can I get from a gas to a liquid? Oh, I'm going to skip gas to a solid for now, right? But I'm going to come back to that in a bit. Now, how can I do it the other way around? If I wanted to go from a gas to a liquid, I would condense that gas. Now, to condense something really means to bring it together, and that's what we're doing to the particles, right? All of these particles are really far apart, so by condensing them, we bring them together into our irregular lattice for a liquid. So let's highlight that over there. Now, how do I get from a liquid to a solid? Well, I freeze it. Freeze. Now, to freeze something really talks about you taking energy away from the atoms themselves. And that makes sense, right? Because these atoms, right, are in irregular lattice because they have a kind of more energy than a solid. Okay, they have more energy, they vibrate more, they can move past each other. If we freeze this liquid, right, we take away energy from those atoms. So suddenly, those atoms don't have a lot of kinetic energy, they don't really move so much, so they stay fixed in their lattice as in a solid. Okay, now, to go from a solid to a gas is a very special type of physical process, and that's called sublimation. Let's write that over here. Sublimation. Now, this is kind of uncommon in the real world, right? But if you look at things like dry ice, okay, so dry ice is what a solid chunk of like carbon dioxide. If you were to just put it on a tabletop, right, you wouldn't get a little pool of like liquid carbon dioxide. You would just see like huge amounts of smoke coming off the dry ice, right? That's because the difference between a solid and a liquid, right, that the temperature range that a substance can exist in a liquid range is so tiny that rather than going from solid to liquid to gas, it just skips the liquid phase altogether and goes straight from solid to gas. Now, to condense something from a gas to a solid is beyond the scope of GCSE, so I'm not really going to talk about it now, but these are all the different states of matter and the physical process associated with that you need to know about. Now, we're going to put a bit more numbers to these things, and we're going to have a look at the graph of changing state. Okay, so now let's have a look at an internal energy graph. So internal energy really talks about the total kinetic plus potential energy of all particles in a system. So let's break this down a bit. Kinetic energy, that's kind of self-explanatory, right? That really talks about the speed at which particles vibrate. Now, we also have something called potential energy. This is the one that usually throws students off. This really talks about the bonds between particles. Particles, I can't really spell, right? There'll be more on that very soon. Okay, now another thing that throws off students is the word system. So system is really just a collection of particles or atoms or molecules, anything really, right? A system just talks about a group of things, okay? So here we're talking about particles, but it could just as easily be atoms as well. Now I have here below an internal energy graph. I know it has a lot on it and it seems kind of complicated, but I'm going to break it down as always. Now on our y-axis we have temperature, which is usually measured in degrees Celsius, and on the x-axis I have heat here. But heat is nothing but energy being supplied into it, and so that's usually measured in joules. Okay, so we really have degrees Celsius against joules. Now if we look at our first stage here, for the solid graph, we can see that the gradient of the line is positive. That means that we're supplying in heat energy here. All right, so I'm going to just call that H1, right? We're supplying in heat energy here, and we're raising the temperature of the actual substance itself too. So when we reach something called the melting point, so that's the point at which the solid starts to transition into a liquid, right? We sort of reach like a flat part on our graph here. So I'm going to say H2 here, right? So H1 to H2 is kind of flat. Why? We're supplying in more heat, but the temperature of the substance isn't increasing. Where's all of our energy going on here? So all of our energy here goes into breaking the bonds between atoms or molecules really, but we'll just stick to atoms here just so it simplifies everything for us. So the energy here being supplied into the substance isn't raising the temperature, it's just breaking the bonds in between the molecules themselves, atoms themselves. So rather than the energy really here is going towards breaking the bonds between the atoms. Then after all the bonds between the atoms are broken, we start to increase the energy. We start to increase our temperature again with the addition of energy again. So we have here H3 right to there. So that's our liquid phase. Now we're supplying heat energy into the liquid phase to raise its temperature to the boiling point. Now at the boiling point, something called evaporation, or rather it's got vaporizing here, but that's really an American word, so we really talk about evaporation in England. So we have now again our graph is starting to flatten out. Now what's happening here? Well, again, all of our energy here is being supplied into breaking the bonds between molecules. So again here, breaking bonds between molecules, right? So we have it there, and then after we fully evaporated it, our temperature again starts to increase, and we reach our gaseous phase. Now you might be thinking, oh, can our temperature increase infinitely from the gaseous phase? Well, actually, in theory, yeah, like we do see gases going to extremely high temperatures, but eventually, as with everything, it does reach a limit. But that's just a bit of extra information for you. So now you really understand how to interpret, and really now, if you follow this logic in your mind, you should be able to draw this graph as well to do with internal energy.